Dear audience, my name is Di Wu. In the following, I represent all the co-authors from University of Leuven in Belgium, as well as Delft University of Technology in the Netherlands, to present our work. Our work is entitled Modeling of Hysteric Nonlinearities in Robotic Catheters Using a Long Short-Term Memory Network for Improved Environment Reconstruction. Our project Atlas received funding from European Union's Horizon 2020 Research and Innovative Program under the Marie Curie grant. Coronary artery disease reduces blood flow to the heart muscle due to plaque buildup in the coronary arteries. It is the most common cause of death globally. The data show that in 2015, around 9 million people died due to coronary artery disease. That means, unfortunately, during my 12 minutes presentation, around 200 people lost their lives due to this disease. Any solutions for this? The answer is percutaneous coronary interventions, abbreviated as PCI. The PCI is shown to be less invasive than open surgical procedure. Some people also name this interventional procedure as catheterization, which indicates the key role of catheters in this procedure. The application of catheter can lead to high success rate for recanalization. However, precise control of catheters still remains challenging at current stage. One of the major causes of imprecision in positioning the catheter tip is the hysteresis. No matter its actuation principles, such as cable-driven or fluidics-driven or magnetic-driven, catheters suffer from hysteresis problem. Hysteresis causes a lag in the output in reacting to the input changes. Moreover, it leads to a complicated multi-value relation between the input and output. Hysteresis originates from an ancient Greek word which means lagging arrival. A system is said to exhibit hysteresis if it has a sort of memory, which means the output of a system not only depends on its current input, but also the historical input. Recurrent neural network was proposed as a tool to process sequential information. It takes historical information into account and utilizes knowledge to predict behavior at future time steps. A long short-term memory network is a type of RNN. Due to their correlation, it is logical to consider the use of LSTM to model hysteresis behavior. The network was showcased and validated on a self-made catheter system. The catheter is driven by a pneumatic artificial muscle. The muscle was attached off-center to the catheter tip. When the pressure increases, the muscle contracts and then applies a bending moment on the tip such that the catheter is bendable. The pressure is regulated by a pneumatic proportional valve, which receives command signal from a PC. A laser distance sensor was used to capture the motion of the catheter tip with a sampling frequency of 250 Hz. The data from the distance sensor is collected by an Arduino microcontroller, and then sent back to the PC via a robot operating system topic. The collected data can be converted to tip bending angle based on constant curvature model. A graphical user interface is created on ROS to facilitate the users to switch among different excitation signals. In order to provide LSTM with data containing diverse excitation patterns, descending sinusoidal pressure was used to excite the system and generate training data. The first type of data is descending sine wave with zero baseline. The data were collected under 4 frequencies, namely 0.2, 0.4, 0.6, and 0.8. The figure on the right side shows the data we collected. It is clear to observe that the hysteresis loops widen as the frequency increases. This property is described as rate-dependent hysteresis. Moreover, one might also notice that there is a dead band at the bottom of the hysteresis loop. In that area, the catheter bending angle almost does not react even though the pressure is increased. To sum up, muscle-driven catheter has a complicated hysteresis pattern, which is described as rate-dependent, asymmetric, and saturated. Another type of training data is descending sinusoidal pressure without zero baseline, which means the pressure does not go back to zero after each period, but only converged to a certain value. The two figures on the right side shows all the training data, containing around 27,000 data points for training the LSTM. A two-layer stacked LSTM was adopted. According to a previous pilot study, a window size equals to 50 showed a good performance while maintaining a low computational cost. Therefore, the input pressure was segmented into a window size of 50. In other words, the sequential pressure data from PT-49 until PT was entered into the LSTM. A fully connected layer was added after the last LSTM cell. Then the bending angle theta at time t can be predicted. The hyperparameters of the LSTM was listed in the table. The network was implemented in PyTorch. The training was performed on a 4 GB GPU. The LSTM was trained for 50 epochs, and the whole training time was around only 10 minutes. The training data were further split into a training subset and a validation set with a ratio of 70% to 30%. The trained LSTM was tested on 4 types of signals as shown on the right figure that contains different patterns such as time-varying frequency, ascending trajectory, as well as arbitrarily varied signals with plateaus. Note that these signal patterns were not included in the training data. In order to form a comprehensive comparison, we choose 2 methods to compare with the LSTM. One of them is an analytical model called deadband rate-dependent Prandtl-Ishlinsky model, namely the DRDPI model. The DRDPI model is a sophisticated and practical model that takes into account the impact of frequencies on the pattern of the hysteresis. In addition, deadband operators in this model allow it to model asymmetric hysteresis as well as saturation exhibiting behavior that appears at the bottom of the hysteresis loops. Therefore, the DRDPI model is fully adapted to model the hysteresis that originates from the entire muscle-driven catheter system. Another comparison model is a traditional machine learning model called spot vector regression, abbreviated as the SVR. The SVR is an expansion of a classical spot vector machine, SVM, from pure classification to regression tasks. Similar to SVM, it is designed for estimation of high-dimensional, nonlinear problems when only a limited number of samples are available. The hyperparameters of the SVR was chosen by using a grid search and a cross-validation method. The results of the preliminary evaluation is shown on this slide. The video of the catheter shows the tip motion. The line plot shows the ground truth, the bending angle predicted by the LSTM, the DRDPI model, as well as their errors with respect to the ground truth. The results of the 3 models were also summarized into a bar plot. 3 metrics, namely the normalized root mean square error NRMSE, root mean square error RMSE, and the maximum absolute error MAE, are used to evaluate the modeling performance. In terms of the RMSE, the LSTM is at least 33% better than the DRDPI model. Moreover, except for achieving a comparable performance in the ascending up-chirp sine wave, the LSTM is at least 34% better than the SVR. Overall, the LSTM is able to accurately model the asymmetric, saturated, and rate-dependent hysteresis originating from the entire catheter system with a sub-degree precision, as well as a lead in the performance compared to the DRDPI model and the SVR model. In cardiovascular applications, the required precision that clinicians indicate as being acceptable is typically in the order of 1 to 3 mm, which corresponds to 2 to 6 degrees if converting to bending angle in our case. The results here show the good potential to satisfy the requirements in terms of precision. The LSTM was further validated in an environment reconstruction experiment by using a forward-looking OCT. Considering that the LSTM and SVR both rely on machine learning, while DRDPI is analytical, and given superiority of the LSTM over SVR, It was found more interesting to compare the performance of the ASTM with analytical DI-DPI in the following experiment. A hollow spherical cap with embedded grooves is fabricated to serve as a dummy environment. This cap is positioned in front of the catheter tip. There are 3 patterns on this object, and each of them covers a circular sector of 90 degrees. The pattern 1 and 3 have 3 mirrored grooves at various distances with respect to the central axis, while pattern 2 is a smooth surface without any grooves. The object is rotated by a DC motor so as to simulate the rotation motion of the catheter. An OCT fiber is attached onto the catheter tip to measure the front distance to the object by using an A-mode scan. This video shows the experimental procedure and the setup. The results reveal that the ASTM can reconstruct the environment with an error below 0.5 mm in all of the 3 patterns. The error achieved by the DI-DPI model is around 3 times larger than the ASTM. The reconstruction experiment validates the feasibility that, with the assistance of the ASTM, a PAM-driven catheter is able to overcome the complex inherent hysteresis and accurately reconstruct the anatomical structure with a forward-looking image modalities in intravascular interventions. Thanks for watching.